Hello, my dear. Welcome to IMS GATE Academy. I hope you are all good and your preparation going to be in a right direction. I am Pragyabrat Tripathi. So we already discussed about the some basic concepts of a thermodynamics, in which we will all things are discussed with the how to apply the first law of a thermodynamics for a closed system, stationary and quasi-static process. Okay, so we already covered few problems, also previous year gate questions also. Now we'll take one next observation, that means observation number third. Previously we will discuss about that observation, that means all the slow process necessarily be reversible or not. We'll discuss successfully for that one. Again we will take a all the isothermal process must be reversible or not. This will all this also we will discuss. We already discussed. Okay, so these things are very important when we analyze the thermodynamics process, right? So this is very important, beta. Now take the next observation, observation number third. Then we will solve some problem, practical application of the first law of thermodynamics, how to decide the operator will say truly or not. Okay, now now we will discuss about the observation number third. See, my dear, see, if this is the special observation, why? Because it gives one property. See, in the thermodynamics we have to discuss already about the first law of thermodynamics. In that we have to discuss one property known as internal energy, right? Now for that particular process we have to develop, we have to develop a second property, that is enthalpy. Okay, so for that one we have to take one observation, right? Take a constant pressure quasi equilibrium process, right? That means see, we'll take a constant pressure quasi static process. Okay, constant pressure quasi static process. Okay, beta, constant pressure quasi static process. Okay, so here we'll take a constant pressure, that means a system with have a constant pressure. That means during the process of the system, all will take a constant pressure process, right? But throughout the process from point 1 to point 2, that means initial point to a final point of the system, during that it execute at a constant pressure, number first. And the process is a quasi equilibrium process, that means a thermodynamics process, right? And which substance? Simple compressible substance. Simple compressible substance, but that means we have to neglect the electrical energy, magnetic energy, surface tension, all this energy will be considered as a negligible, okay, as compared to another form of energy, right? So for that one we have to draw a system. Okay, so for the simplicity we take a system like that. Okay, for the simplicity we have to take a system like that. Okay, what is that? This is our system. Let's suppose this is our piston cylinder arrangement. Okay, this is our piston cylinder arrangement. This is our cylinder. Okay, take this is our cylinder. Okay, and this cylinder, this is our cylinder, and this is our piston. Okay, we'll take this is our a piston. Okay, 1 second, beta. This is our piston. This is our piston. Okay, this is our piston. This is our one cylinder, and this is our piston. Okay, this is our piston. Okay, this is our piston, which will move at a constant pressure. Okay, that means why it, how to it will move the constant pressure? The process during that movement of the piston, will take throughout inside the gas, inside the system, the pressure is remain constant. Why the pressure remains constant? Why? Because the resistance pressure is constant. What is the resistance pressure? Atmospheric pressure, it is constant, and weight of the piston, it is also constant. That means force due to the atmospheric on the piston and weight itself by the piston is a resistance pressure, and that pressure throughout the process is constant. So accordingly the system pressure is also constant. That means this is our system, this is our system beta, this is our system. Let's suppose this is our system, this is our system, okay, this is our system. Let's suppose this is our system, this is our system, okay, this is our system boundary, and in this system, okay, so this is our system, this is our system, and this is our system boundary. How to move the piston? There must be external energy will supply. How to move this piston? That means the system have a state point 1 and it will go to state point 2. How it will go? There must be energy will supply. So let's suppose we supply the energy to the system. Let's suppose we apply the energy to the system as a heat, as a heat, as a heat. We'll supply the energy to the system as a heat, okay. This will supply the energy into the system as a heat. That means we supply the energy as a heat. That means Q in, okay. There is Q heat in. We supply the energy. That means if we heat the system, system will try to expand. During the expansion, there is no change in the resistance pressure, so that the piston will move at a constant pressure. So that the piston will move at a constant pressure, okay. And during that, the piston will move in a very slow manner. That means quasi-static process. The piston will move upward, the very slow process. So let us say piston. What is it that? Let us piston moving in a quasi equilibrium process. Equilibrium process, okay. Process. It will move in a quasi equilibrium process, so that pressure inside remain same. Why it is same? Because why it is same, beta? There is one question mark. Why it is same? Because resistance pressure one second, because the resistance pressure, okay, because the resistance pressure which is combination of P atmospheric plus weight of the piston will remain same, will always same, always same. So inside pressure also same, okay. So this is our modification in which we have to modify that the system will execute from point 1 to point 2 through a constant pressure, right? This is our the situation, okay. Now we apply the first law of thermodynamics. Now we apply the first law of thermodynamics. What is that? See, my dear. Now we apply the first law of thermodynamics. What is that? we apply the first law of thermodynamics. See, my dear, we apply the first law of thermodynamics. Okay, we'll apply the first law of thermodynamics for this system. That means first law of TD. Okay, we'll apply the first law of TD. What is that? What we know that? We know that first law of TD, dq, it is visible, dq is equal to du plus dw. What is the assumptions of this equation? This is for the closed system. That means there is no any energy transfer according to the mass. Only the transfer is heat and work, and we disregard the change in kinetic energy and potential energy. That means stationary system. That means this is the first law of thermodynamics for a closed system of a stationary system for a simple compressible substance. Okay. Now the process 1 to 2 will integrate from point 1 to 2 dq is equal to u2 minus u1 plus 1 to 2 dw. Okay, no problem at all. Now this is for any process. This is for any process, either reversible or irreversible. But once we defined the work, that means we can write q1 to 2 is equal to u2 minus u1 plus w1 to 2 after integration. Better you can write here. It's better you can write also integration, no problem at all. That means integration 1 to 2 du. Integrate this one. So if we integrate, this is the property. So u2 minus u1. This is the transfer. So q1 to 2, w1 to 2. Now this equation is applicable. This equation is applicable. Which condition? This equation is applicable for both process, either reversible or irreversible. Number first. But this is for the closed stationary system of a simple compressible substance. Okay. Now, if we define the work as a PdV work, why? Because when the piston will move up or down, there must be a displacement of a boundary, system boundary. That means if you define the work as a PdV work, in that condition, this equation is applied only for the reversible process. That means this is for the stationary system, right? This is for the stationary system, okay? Stationary system, okay? This is for the stationary system. No problem at all. No problem at all. Now, beta, now we define the work. We defined the work. That means if we take this as a PdV, that means work 1 to 2 is integration PdV. That means take work 1 to 2 as a PdV. Okay. Now we know, we already says that pressure is constant. Okay. That means this P is constant. According to your statement, the pressure is constant. So we will kept outside. That means P integration final volume minus initial volume. Okay. This is given in the statement. Right. Put this value inside this equation. So what is that? Q1 to 2 and rearrange this one. So this is U2 plus P2 V2 minus U1 plus P1 V1. It is right? Rearranging. We are doing nothing. We are just rearrange. Put this value inside this equation and rearrange this. See, my dear, one thing is that when we have comfortable to rearrange it, when there is a constant pressure. If there is no any constant pressure, if there is no constant pressure, then we cannot write like that. That means what is that? This is the property, U is the property, P is the property, V is the property. So this is the property at point 2 and this is the property at point 1. This is the property at point 2, this is the property at point 2, 1. That means what we have to transfer a heat to the system that will create the change its property of the system. That means system property 2 minus system property 1. And that property is known as change in enthalpy. That means this is known as change in enthalpy. This is known as change in enthalpy. Change in, this is the birth of the enthalpy. Change in enthalpy. So we can write like that, delta H is equal to H2 minus H1. This is your H2 minus. That means what is the heat will transfer Q1 to 2 during pressure constant of a closed system, it will transfer the change in enthalpy. This is the very important. So my dear, there is a one confusion for the student community, in the student community, is that, sir, this equation is applicable only for the open system. No, this is not like that, okay? This is not like that, okay? So, see beta, heat will transfer at a constant pressure is equal to change in enthalpy, and that change in enthalpy H2 minus H1 is the property, and that is for the any process. But the process followed by the constant pressure. That means change in enthalpy H2 minus H1 is for any process, but the change in enthalpy is equal to exactly as a heat transfer only for the constant pressure process. This is very important. I repeat, very important. See, change in enthalpy, why? Because enthalpy is the property. That means change in enthalpy H2 minus H1 is the for any process. Is the any process, either reversible or irreversible. For any process, any system. But that change in enthalpy is equal to heat transfer at a constant pressure only when there is a quasi-static process and constant pressure process of a closed system. This is very important. So this is very important. So we can write like that. What is that, beta? That means heat transfer. That means heat transfer during the process 1 to 2 is exactly is equal to change in enthalpy. Okay, change in enthalpy, okay. So this is one. So this is your change in enthalpy, very important. This is your change in enthalpy. This is very important, beta. I am telling you, important. What is that? Why it is important? Why? Because so change in enthalpy, change in enthalpy is not valid for, very important, valid for constant pressure, process. Why? Because it is a property. It is a property. Because it is a property. It is a property, okay, and valid for any process, and valid for any process, valid for any process, okay, valid for any process. This is number first. But the change in enthalpy is exactly equal to the heat transfer only at a constant pressure. This is very confusing. Why? Because a student get confused, sir, ki enthalpy always valid for a constant pressure. No, that enthalpy come exactly equal to heat transfer. That means this enthalpy exactly is equal to heat transfer when the pressure is constant. But the change in enthalpy for the any process, number second. But this change in enthalpy, but this change in enthalpy at a constant pressure always gives heat transfer. Very important. Always gives heat transfer. This is very important. Always gives heat transfer. So, my dear, we have to come into two property. First, see, first one is change in internal energy. Okay, change in internal energy. That means delta U. Second one is that change in enthalpy. Enthalpy as energy. Internal is energy. Enthalpy, it is also energy. Change in enthalpy. That means delta H. So, my dear, these two are, that means this change in internal energy and change in enthalpy is for any process. Why? Because it is U. What is that? U2 minus U1. Yes or not? U2 minus U1. And this is also H2 minus H1. Very important. That means if this is your process, if this is your thermodynamic plane, beta, see, if this is your thermodynamic plane, if this is your thermodynamics plane, let's suppose, if this is your thermodynamics plane, any property, let's suppose any property X, this is Y property and this is X property, any property X and Y, and this is at the thermodynamics plane. When the properties are fixed, that means if this is point number 1, so at this point internal energy and enthalpy is fixed. That means at this point there is enthalpy H1 and internal energy U1. At point 2, there is enthalpy H2 and internal energy U2. So this is fixed. And you can join these two pressure process, either constant pressure, constant volume, constant temperature, any process. That means you have to draw in between this for any process. That means this is A, this is B, and this is C. For any process, beta. For any process. That means internal energy and enthalpy is a property, and that change in a property for any process. Okay. Number first, this is the property. This is the property relation. Very important. This is the property relation. Like a pressure P2 minus P1. So if you change the pressure, the change in pressure for any process, change in volume for any process, change in internal energy for any process, change in enthalpy for any process. Okay. So now our job is, what is the relation between enthalpy and internal energy? What is the relation between enthalpy and internal energy? So if you divide the mass, this is the specific internal energy. If you divide the mass, this is a specific enthalpy. Okay, so just now we see that we have to already see that enthalpy is equal to internal energy plus PV, internal energy plus PV at that point. So at this point, what is the relation? Enthalpy H is equal to U plus PV. What is the enthalpy H2? U2 plus PV. That means if you have internal energy, you can easily find the enthalpy at this point. If you have internal energy at point 2, you can easily find the internal enthalpy at point 2. Okay. So what we know that, hence, what is the relation? Enthalpy H is equal to internal energy plus P into V. P into V is also energy. This is also energy, this is also energy. But this energy are a property of relation, like a PV equal to MRT. PV equal to MRT is the state postulate. Hi Sita, how are you? Okay, so PV, H is equal to U plus PV. So H is the enthalpy, U is the internal energy, PV is the work, is the energy. So these are the state postulate. These are also a state postulate. Okay, great. So these are the internal energy, these are the enthalpy. So when we have any information, why? Because pressure and volume is the primary property. It always given in the question. If you have a pressure and if you have a volume and if you have internal energy, you can easily get the enthalpy. You can easily get the enthalpy. Now, if you divide the mass of the system, H divided by mass, U divided by mass of the system, PV divided by mass of the system. What is that, beta? H divided by mass is a specific enthalpy, U divided by mass is a specific internal energy, and PV divided by mass, that means V divided by mass, P into a specific volume. So these are the very strong equation. This is the very strong equation I am telling you. Okay, so these are the very strong equation, beta. So if you have any property, that means if you find the enthalpy at point 1, what is the internal energy at point 1? What is the plus? What is the pressure at point 1 into what is the specific volume at point 1? Add this, you can easily find the enthalpy at that point. You can easily find the enthalpy at that point. So beta, this is called a specific enthalpy. This is called a specific internal energy. This is P into a specific volume. So mind it, there are very important things. Change in enthalpy, that means, see, enthalpy or internal energy, it's a property. That means it defines the system. It defines the system. So change in a property for any process. Change in the property for any process. Change in the property for the any process. But if you talk about the change in enthalpy, what is the change in enthalpy at a constant pressure? That gives the heat transfer. That means heat transfer, it is a path function. It is exactly equal to the point function when there is a constant pressure. That means if there is a process, if there is a system, and system will execute at a constant pressure in a quasi-static manner for a simple compressible substance, during that process, the change in enthalpy exactly equal to heat transfer. That means if you define the change in enthalpy, what is the heat transfer? That means if you define the change in enthalpy as a heat transfer, you have to must be a constant pressure, otherwise you cannot define. That means change in enthalpy, change in property is equal to path function, is equal to heat transfer only at a constant pressure, only. But change in enthalpy for the any process, change in internal energy for the any process. Why? Because this is the state property. This is the state variation. This is the state relationship. This is the state, this is the property of the system, and property of the system for any process. It is clear? It is clear? It is clear, everyone? Please. It is clear, beta? Okay. Now, if it is clear, so we take the another shot. So this is the observation. So what is the observation? This is the observation. What is the observation? Ki sir, a constant pressure quasi-equilibrium process for a simple compressible substance, if you supply a heat transfer, that heat will be responsible to change its enthalpy. Change its enthalpy. Okay. So this is the one observation. That means system will execute at a constant pressure. That means you made a system like that, it will expand or contract through a contract. That means it will compress or expand. The system will either compress or expand. During the compression and expansion, if the pressure is constant, now you supply a heat, that heat will be responsible to increase or decrease the enthalpy. So enthalpy, internal energy of the system may be increase, may be decrease. It is not like that, sir, it is always increase or always decrease. No. So my dear, very important, very important. Many students get confused here कि sir, when we think about the internal energy and when we think about the enthalpy, sir, internal energy is valid for the closed system and enthalpy change valid for the open system. No, it is wrong. This internal energy change and this enthalpy change, these are the system property and these are for the any type of the system. Any type of the system, any process. Any type of the system. Why? Because this is a change. If you draw the process in between 1 to 2, either irreversible, that means U1 equal to U2 minus U1, H1 equal to H2 minus H1. These are the property change and these are the responsible for process A, process B, process C, any process. But this change in enthalpy is exactly equal to heat transfer only when there is a constant pressure. So if A, B and C in this process, if any one of the process is at a constant pressure, so that constant pressure is responsible for the heat transfer, otherwise not. So if you want that the change in enthalpy is, sir, gives the heat transfer exactly, there must be a constant pressure process, otherwise not. Otherwise not. Okay. So this is the one observation which is very important. So now we solve this one problem for that one. Okay. See this one. See this one, beta. A piston cylinder device contains helium gas. Okay. Helium gas, initially this is your 1 kilopascal. Initially this is your 1 kilopascal, 150 kilopascal and 20 degree centigrade, and volume it is given 0.5 meter cube. Okay. Helium is now compressed. That means you apply the pressure on the piston so that helium get compressed. And what is the compression process? Polytropic process. PV per power n is equal to constant. This is the compression process. Okay, this is the compression process. PV per power n equal to constant. What is the intensity? How much the intensity you have to compress? The compression is initially 150 to 400 kilopascal. Yes, if you compress the gas, the pressure will increase. Yes, 400. Initially pressure 150, final pressure is 400 kilopascal. And if you compress anything, obviously the temperature will increase. It may be increase or maybe decrease, but it will increase. Why? Because there is a ideal gas. That means if there is an ideal gas and there is a no chance of heat transfer, yeah, there may be a very less chance, very minimum chance, that means very less magnitude of heat transfer as compared to the compression. The force, that means you compress the system, that force is responsible to suit the temperature. That means temperature will increase. Determine the heat loss or gain during this process. That means what is the heat loss or gain? See beta, there is a one important thing. There is a one important thing. What is that? What is that? if you compress anything, there is not necessarily that it will always increase the temperature. It may be decrease. This is very important. If you compress a system, you cannot surely say that, sir, while the compression, always the temperature will increase. It may be decrease. One, if you compress it and the temperature will decrease, obviously the heat will gain by the system. Second, if you compress anything and its temperature will increase, obviously heat will lose. So there must be a high temperature. That means initially there is 20 and there is a temperature. So the temperature will increase and that increased temperature will lose the heat. That means in this question, heat will lose. If heat will lose to the system, that means if heat will reject to the system, that heat is a negative. Okay, so what is the final result outcome after solving this problem? The heat is a negative quantity. Okay, so we'll try to solve it, no problem. See beta, we'll try to solve it. So there is a this is your cylinder and this is your piston. Okay, this is your piston, and in this piston there is a system. Let's suppose this is our system. In that system there is a helium. There is a helium, and when it will compressed, there is a compression. Okay, there is a compression. When it will compressed, the compression process is equal to P V पे power n is equal to constant. That means polytropic compression. Now beta, during that compression, let's suppose heat will in. Let's suppose. Why? Because we take a positive sign. Now, any system, if there is any system, and for the heat, Q in is positive, work out is positive. Work out is positive. These are the main things which you have to consider. Work out is positive. So these are the positive quantity and these are the positive quantity. So we have to solve in the positive manner. So let's suppose while compression, heat will receive Q in. These are the models. Why? Because we have to assume the sign convention when the heat into the system is positive and work out to the system is positive. So we have to take this sign convention. Automatically, you can analysis according to this sign convention. If this is a negative, that means heat will out. Our assumption is wrong. Initially, we have to take a positive sign. Q in is a positive sign, but after solving, if Q in is negative, that means heat must be out from the system. Okay, so we have to solve it. The property it is given, take. What is the property it is given in the question? The property is it is a given. What is that? R value it is given. Gas constant it is given 2.0769 kilopascal meter cube per kg Kelvin. It is given, okay, and also a specific volume it is given at a constant volume. It is given 3.1156 kilojoule per kg Kelvin. It is given. It is given in the question. No problem at all. Okay. Now we have to calculate the heat transfer. So we apply the first law of thermodynamics. See, my dear, first law of TD. What is that? What is that? During the process Q1 to 2 is equal to U2 minus U1 plus W1 to 2. These are the fundamental relations. Why? Because there is no any mass transfer. So we have to take only heat transfer and work transfer. My dear, you have to assume like that ideal gas behave, helium gas behave as an ideal gas. So for the ideal gas, change in internal energy is equal to C beta. This is the very important things. Always remember like that. For the ideal gas, change in internal energy delta U is equal to m CV delta T. Change in enthalpy is equal to m Cp delta T. These are the two relations. Always remember. Okay. For the ideal gas, this is for ideal gas. For ideal gas. For ideal gas. And for ideal gas. And yes, helium act as an ideal gas. Helium act as an ideal gas. Number first. Number second, the compression and expansion of the process is quasi-equilibrium process. What is that? Very slow. If it is not given, quasi-equilibrium process. Okay. Okay. And there is no mass transfer. Also, no mass transfer. That means it is a closed system. That means this is a closed system. This is for the closed system. Now, first, if you put the value of internal energy, mCV it is given, delta T also given, T2 minus T1, but m it is not given. M it is not given. Number first. Why? Because you have to find this one. So for the finding of this one, you have to find m. That means you have to put like that m CV T2 minus T1. So CV it is given, T2 it is given, T1 given, but m it is not given. So first find mass of the system. Now, if there is a quasi-equilibrium process, so it is integration 1 to 2 P dV. Volume it is given, initial volume and final volume, but pressure it is not given. Pressure it is not given. Pressure it is given, but how to find this? Why? Because pressure, this, when we solve this integration, when there is a pressure and volume relationship it is given. So for the polytropic process, this we have to knowledge about that. What is that? P2 V2 minus P1 V1 divided by 1 minus N. Okay, 1 minus N. And during that, C beta, if you apply this equation, now if you apply, so first we find the mass. First we have to find the mass of the system. And this is fixed. Mass of the system. And this is fixed. Why? Because this is a closed system. So what is the mass of the system? M is equal to P1 V1 by R T1. You have this one. So what is P? You have P, it is given 150 kilopascal. What is V1 initial volume? 0.5 meter cube. R it is given 2.0769 into temperature. This temperature is always Kelvin. Very important. It is in Kelvin. Don't confuse. So if you Kelvin, that means 20 plus 273, 293. 293. Solve this one. This is your 0.123 kg. So this is your mass of the system. Okay. That means this mass will present in the system while in the compression. That means you compress this mass. That means this is a mass that will responsible to compressed. Okay. Now, there is no any final volume it is given. Yes or not? See this one? No final volume it is given. See, initial volume it is given, but there is no any final volume it is given. So we have to find the final volume. So what is the final volume? We have to find the final volume of the system. That means second, this is first step. What is the second step? Final volume of the system. Final volume of the system. That means after compression. After compression. How to find the final volume? Just think. Just think how to find the final volume. Why? Because this is the ideal gas. So we have to know that PV is equal to mRT. M is a constant. This is fixed. Fixed. So we have to P1 V1 by R T1 is equal to P2 V2 by R T2. This relation. So R is same. So what is V2? We have to find it. So from here, V2 final volume of the system. Final volume of the system is, if you find final volume, there is T2 P1 by T1 P2 into V1. Put all this value. T2 final temperature we have, yes or not? We have final temperature 140. This have a final temperature 140. So 140 plus 273. It is in Kelvin. Okay. So put this one. So T2 is, if you put 413, P1 we have 150, T1 you have 293, P2 you have 400 into volume. This volume we have 0.5. Solve this one. If you solve, this is 0.264 meter cube. So these are the final volume of the system after compression. See, initially volume is what? Initial volume is 0.5 meter cube. Initial volume is 0.5 meter cube. After compression, volume is less. Yes, volume is less than 0.5. That means this must be a compression. Right. Now, if you find the final volume, we have, what is the process? PV per power n is equal to constant. But here it is, this is your polytropic index. This is your index. It is not given. How to find? Yes, very simple. P1 V1 per power n is equal to P2 V2 per power n. P1 you have, V1 you have, P2 you have, V2 you have. So from here you can easily find the polytropic index. Polytropic index n, and that polytropic index n comes to be 1.536. Now all the information you have. Now, but we have to find this work. Then we put this equation in this equation. So how to find this work? While the compression is a quasi-static. So how to find this work? See, my dear. Now, this is the, if you compressed it, there is a work in. If you compression, there is a work, boundary work in. And if there is anything which is in the form of work, which is in, is anything in the form, if work is a form of energy which is into the system, that is negative. that is negative. So, boundary work in, that means W B in, put negative sign, V1, V2, P dV, and we know that for the polytropic, minus P2 V2 minus P1 V1 to power 1 minus n. This we have from the basic. Okay, now put this value, but we don't P1 V1 P2 V. It is easy to put PV is equal to MRT minus MR. We can write also T2 minus T1 divided by 1 minus n. We can write like that. We have a temperature, so minus we have a mass 0.123, we have a gas constant 2.0769, we have a temperature difference 413 minus 293 divided by 1 minus, we have a polytropic index 1.536. Yes or not? You calculate also for this formula. P2 you have, V2 you have, P1 you have, V1 you have, 1 and n you have. You can easily calculate. But I prefer this one. Why? Because this will be little bit less calculation. Okay. Put this value. Put this value, beta. This is your 57.2 kilojoule. This is your in. This work is in. We can already take a negative sign, so it is a positive. Okay, this is work is into the system. Now we have to apply the first law of thermodynamics. What is that? We know that energy in minus energy out is equal to delta E of system. This is responsible to change in energy, and this is responsible to change, this is your energy transfer and this is your energy change. That means net energy transfer, net energy transfer through by heat, work, mass. Okay, and this is your net energy change, net change in energy by kinetic energy, potential energy, etc. Okay, so a change in energy by kinetic energy, potential energy and internal energy also. See my dear, there is no mass transfer, this is 0. Non-flow system, non-flow. Change in kinetic energy, change in potential energy, this is 0. This is called a stationary system. This is called a stationary system. So what is the equation? Only heat. So heat is in, Q in. It is in minus work is out, but if you compressed it, there is a negative work be in is equal to change in internal energy delta U, that means M U2 minus U1, delta capital U. So what is, so this is your Q in plus WB in is equal to M R. This is your R. M, this is your U, CV T2 minus T1. T2 minus T1. Put Pratik. Put this one. Put this value Q in. We have to find it plus. What is the work? Work we already calculated from here, 57.2. 57.2 is equal to mass we have. How much mass? Mass is 0.2, 0.123. T2 you have 413. T1 you have 293. From here you can get minus 11.2 kilojoule. This is your answer. So my dear, what is the importance? Why we solve this problem? Why? Because you have to confuse your sign convention. Apply this equation. Accordingly, you can follow this one. In is your heat. Already, if you take a negative sign, so there is a positive. If you take this is a positive sign, so there is a negative. So negative heat in is negative. That means what is the conclusion? The conclusion is that no, heat will not in, heat will reject at this magnitude. Okay, so please keep in mind this problem is very dangerous problem where the sign convention is strongly mixed with this problem. Okay, if you do any mistake, you 100% chance to wrong calculation. Okay, it is clear? Everyone please, it is clear beta? Everyone please, it is clear? If it is clear, then we'll go to the next things. What is that? This is your things. See this. First law applied to open system. This is very important. Why? Because why we take this one? Why? Because if you don't know this open system application, you cannot get any. Why? Because this is the actual. Why? Because all the engineering devices are open system. That means turbine, compressor, blower, fan, heat exchanger. All these are the open system. So this is the most practical situation in which apply the conservation of energy. So for the open system, name itself suggests that sir, this is the open system, and so for the open system, there's something mass in the terms of mass will in or something in terms of mass will out. Yes or not? Yes or not, please everyone? That means this is an open system. Very important. This is your open system. That means the energy not only associated with work and heat, energy also associated with the transfer of mass. So we have to take a open system. These are the, let's suppose this is the open system. There is inlet and there is a one exit. What is the importance? This is a very important thing. There is an inlet and there is an exit. So this is our open system. This is very important. This is our open system. That means this, and we take this is our cross section which is in, and this is our cross section which is out. So this is I, and this is exit E. That means there is a something will into the system and there is something will out from the system. What is the in or out? The mass. Let's suppose in this situation the energy, positive sense, heat will into the system, Q in. We take at a rate basis, watt, joule per second, and work is out from the control. This is a control volume work. Work out. Okay, work out. This is the control volume work. That means while fluid in or exit, the system will perform a work and take a heat in the general form. In the general form. Okay. Now, what is the importance of this one? See, beta. What is the important assumptions behind this while deriving this energy conservation for the open system? What is the important assumptions? This is the interview question. What is the very important information while we derive this equation? Main assumptions. Please, anyone. What is the main assumptions while we derive this equation for the open system? What is the main assumption? These are the interview question, hot cake interview question. What is that? What is that? This is the very important information. So, these are the very important information. Why I am telling you now? This thing you are always missing. No, Pratik. Radiation effect are not taken place. No, it is not like that. No. You are wrong. Next. See, this I am telling you 99% if you read the open system, if you read the thermodynamics, but you can get confused. What is the important assumption? Please, anyone? Please, anyone, I give you a challenge. Please, anyone can tell. Who are listening this lecture, anyone can tell. I am telling you, these are the very important. That is the very important assumptions while we are deriving the open system. So, think I will discuss. So, I will discuss you. See, this is in, this is exit, while its property of the open system 1 to 2 will change. Okay. Now, what is the assumptions? Very important, I am telling you. What is the important assumptions? Please, anyone? Please, anyone, please. If you read the thoroughly thermodynamics, please reply. If you know the thermodynamics, please reply. Otherwise, you just study, not feeling. This subject is try to feel it. Okay. See, beta, there is a very important assumption is that while the quantity will in or out, at that cross section, the properties are uniform. That means the property will not change while it will enter to the cross section or exit from the cross section. You may think that, sir, what is happening if you are don't know, so there is no any problem. Yes, it is a problem. While we solving the problem, one question I will solve in the next session, there must be a mistake if you don't know this assumptions. And there is also gate question for that one. So, assumptions properties are properties, any properties. Properties are uniform across each flow section. And what is the section? I and E. Very important. This is very important, I am telling you. I already told that I and E are the naming of the cross section. 1 and 2 are the naming of the property. That means this is the 1 is the property, initial property, and this is the final property 2. There is an inlet is the cross section. That means any property while entering or exit are same. That means it is not changing during the entry. That means what is the pressure at Pi is the same. What is the, that means what is the mass Mi? It is uniform throughout the cross section. It's like thermal conductivity remains yes, you can say that for the open system. It is not like a conductivity beta. Conductivity is a property. Yes, it is a property. But see, yes, if there is a fluid and fluid have a conductivity, thermal conductivity, fluid have a conductivity, that conductivity will not change at that cross section. At that, see, this is our cross section now. This is our cross section, and this is our cross section. Yes or not? This is our two cross section. This is cross section I. This is cross section E. So while entering something, the property are same through each point at this cross section. It is not changing. And the property is same at this cross section. It's not changing. That means at that cross section, the properties are same. That means uniform at any location. At any location, location 1, location 2, location 3, it is uniform throughout at that cross section. This is very important, I'm telling you. Either any property. It is clear? It is clear? Everyone please? So these are the very important assumptions I'm telling you. That means properties are uniform throughout the cross section while it enter or exit. These are the main assumptions. Okay, now. So, see beta, throughout the engineering, there are three conservation equations. There are three conservation equations. If there is a flow anything, that means there is a mass is in, the mass is out. That means there is Mi, mass flow rate in, and there is a mass flow rate exit, Me. That means mass what is in and mass what is out, exit, that will deals with the conservation of mass. That means first conservation is conservation of mass. If you find force while entering or exit, that will calculate conservation of momentum. Number second. Number third, while you consider during the flow in or exit, if you find the energy, that is called conservation of energy. So there are three conservation throughout: conservation of mass, conservation of momentum, and conservation of energy. So conservation of mass in this equation gives the continuity equation, volume flow rate. Conservation of momentum gives the force equation. In the fluid mechanics, Euler's equation. But in the thermodynamics, we cannot bother about the force. So we cannot take about the conservation of momentum. But if you bother about the energy, the conservation of energy. So there are two conservation of energy. Conservation equation. Conservation equation. What is that? Number first, conservation of mass. Number second, conservation of energy. Okay. Conservation of mass. Why we consider in this system as a conservation of mass? Why? Because this is the open system. In the closed system, we cannot bother about the conservation of mass. Why? Because there is no anything flow in, flow out. So we don't bother about the conservation of mass. Only we are bothering about the conservation of energy. So what is the difference between the analysis of the closed system What is the difference between the while analysis of the open system with respect to closed system? In the closed system, we cannot consider about the conservation of mass. Only we are considering about the conservation of energy. But while we analyze the control volume, control mass system, control volume system, open system, one extra conservation of equation will add, that is conservation of mass. So what is the difference while applying the first law of thermodynamics for the control mass system and control volume system? Ki sir, control volume system, one extra component of conservation will add, that is conservation of mass. If you disregard the conservation of mass system, that analysis is same as the closed system. So this conservation of mass, while we considering the conservation of mass, that will decide you have taken as an open system. Okay? It is clear? It is clear? It is clear? So, while we are deriving this equation, we have to bother about the two conservation. This will already done. Conservation of energy will already done. First law of thermodynamics for closed system. For the closed system or open system, conservation of energy there. Why? Because the energy will transfer. If there is a closed system, if there is an open system, there must be a conservation of energy. That means energy will transfer. But while we are considering the open system, one extra conservation equation will come into picture, that is called conservation of mass. Yes or not? Yes or not? Okay. So what is the conservation of mass? Sir, conservation of mass is that mass flow rate in minus mass flow rate exit is equal to change in mass with respect to time for a control volume. This is your conservation of mass. Now, my dear, if this system is steady, that means the property of the system is not changing with respect to time, then dm by dt of a control volume is 0. So, first law of a thermodynamics for open system and system is steady, we have taken into account. So, if the system is steady system, then dm by dt of the system control volume is equal to 0. So, my dear, the second assumption we have to analyze. This is the assumptions. No, dm by dt is if there is accumulation, that is unsteady. We'll charging and discharging of a tank. Yes, you are important, very important, Pratik. So, in the first law of thermodynamics, there are three topics. One is the conservation of energy for the closed system. Second is the conservation of energy for the open system. And third, conservation of energy for the open system while the fluid in or out, there must be a property change with respect to time. In that we can consider this is not 0. Yes, you are right, Pratik. dm by dt is accumulation when there is a unsteady flow system. That means charging or discharging of a tank. That means if you consider dm by dt of a control volume is not equal to 0, that is for charging and discharging of a tank. Charging or discharging of tank. That means in that condition, the mass of the system, control volume system, will changes with respect to time. So the first law of thermodynamics have a three kind of approach. First approach, there is no any conservation of mass, that is called closed system. Second approach, there is consider the conservation of mass, that is open system. Third is conservation of mass is also a conservation of energy also, but the control volume system have a change its mass with respect to time. That is the three aspect. First first law of thermodynamics for closed system, second is called first law of thermodynamics for open system, third is called first law of thermodynamics for unsteady system. First law of thermodynamics for unsteady system. It is clear? It is clear? It is clear now? Now, in the next session, we'll derive this little bit and we go further and we enter and try to solve some numerical problem, and along with we will enter the second law of thermodynamics. So keep in mind beta, in the thermodynamics there are three components. First, basic introduction part, first law, three component. One is we are not considering the mass conservation, only energy conservation. Second, we are consider the mass conservation, but there is no any accumulation of mass within the system, that is called steady system. Third one called must be accumulation of the mass during the flow in or out when there is a steady system, unsteady system. Okay? Okay, beta? Okay? So we'll consider in the next session, next upcoming session, there is an analysis and try to solve one best problem of a previous year, very tough problem, previous year GATE question, and also will enter the unsteady system and second law of thermodynamics. Okay, thank you. Bye-bye.